Welcome back everyone. In this session, we are going to thoroughly check the output that has been given by the Abaqus. So first thing, we will start with the displacement. Simply go for the U, go for the contour, and let us go for the animation. Now under the animation, we have three types. One is the scale factor which will be applicable for single frame. Other one is the harmonic which will go up and down. And another one is the time history. Since we are performing the multi-step analysis, in such cases it is always better to go with the time history. With the time history, it will start from the step 1, go to the step 2, and again it will repeat the procedure. Now observe the animation properly. If you want, you can reduce the speed of the animation also. So we can go for this option. Let us reduce the speed. Go for apply and go for OK. Let us increase the speed little bit. Okay, no, this is sufficient. Observe the animation properly. Take your time. From here, the engagement have started. It went ahead. Then it came in contact at this location. And again the disengagement has started. Once the displacement animation is clear, let us pause the animation and let us have a look into the stresses. Let us go for the stress. Let us try to hide the one component. So I will simply go for the remove selected. Let us go for the element. Let us go into the particular view. Let us say by angle. Just select it and press middle button multiple times. Automatically the entire top instance will get removed. Or we could have gone with the part also. But as of now, let us focus on this animation and let us play the one. Try to observe where we are getting the maximum stress. For this particular component, there are two locations where we might get the maximum stress. Here, we have applied the boundary condition on the top face, so this region is going to be stiffer one. In addition to that, in this particular region, we don't have any fillet. So the regions where we might have the high stresses is this one and this one. So basically two sharp corners. You can check the maximum amplitude of the stress is 210 megapascal. If you want to show the value of maximum stress, we can go for the option, go for contour, go for limits, and here let us click on the show location, apply and OK. If you want, you can pause the animation. Then let us go for the result step and frame. Then let us go for the push step. Go for the last increment. Go for apply and go for OK. So at the end of the step 1, that means at the end of the push step, in this location we are getting the stress of 4 megapascal. So essentially in this particular analysis, the maximum stress we are getting in between, not at the end of the step. In similar way, let us say reverse and let us observe what is happening with the insert as well. Let us play the animation now. So here also you can see this location is more prone to the high stress value. If you want to check the result frame wise, we can again pause the animation and then you can click on the next frame. So from here we can go to the next frame. Again let us go to the next one. Okay, before this one. So you can note at this location we are getting the stress of around 244. Again we can go for the next. You can note over here currently we are in the pull step and the increment is 0.8895. Go for the last. You will get at the pull step and the increment of step 1. Now from here, if you want, again you can go for the step and frame, push step, go to the first increment, apply and OK. And again you can go frame wise also. Hope you clearly understood how you can check the stresses. Let us remove this location identification by going to the options, contour, limits, and let us remove this show location button. In addition to the checking stresses, another very important factor is to check for the contact pressure. So let us go for the C press and now let us play the animation. You will note wherever the contact is happening, that particular area is highlighting. So indeed, from the animation, it looks like the contacts are taking properly. Let us again go for all. Now try to observe the animation on the buckle also. You will notice that the red spot will move in the downward direction in the push step. Okay, looks like we are not able to see it properly. So let us remove few of the element by going to the element and let us go for part instance, select the insert and go for done. Now let us wait for few seconds. So you can note the contact is taking place properly. And again now it will remove the contact. Once it is done, you can show all the things. One of the better way to see the animation when the components are overlapping is to go for the wireframe. Simply click on this button and let us click on this scroller and let us remove it downward. And now you can see wherever the contacts are taking place, it is showing in the highlighted color. I hope you got the point. So with respect to the displacement, stresses and the contact pressure, everything looks appropriate. Now only thing that has remained is to calculate the push and pull forces. To do that, we are going to make use of history output. If you remember, we are applying the displacement in this location. So let us imagine like this. You are pushing the insert into the buckle using your hand. Once you try to push the insert into the buckle, you will feel some resistance. So if we calculate the reaction force which is coming at the location where we are applying the displacement, that particular force is nothing but the push force and pull force required to engage and disengage the insert. To calculate that force, we can simply go for the history output. From here, there are two options, either go with the history or go with the field output. So as of now, let me go with the field output because from here I can see the resultant forces. So let us go for field 1, go for continue. Under the variable, let us go for unique nodal and let us go with the magnitude of the reaction force. In addition to that, let me click on this RF2 also. So essentially, there should not be much difference between the magnitude and the RF2. So I have switched on both the things. Then I will go for element and node. Click on the node set. And here we have already created the loading point as a set. So I will click on it. Then simply go for the plot button. Now let us move this one. So you can see over here it is exactly mirror image, which essentially indicate RF2 and the magnitude of the reaction force are more or less same. So in order to avoid the confusion, let me again go for the field output and let us remove the RF2 and let us look for the magnitude only. Now let us close the animation. Let us see what will happen if I try to play it. So over here you can see I am getting this yellow color line. Let me go for the viewport. Let us go for the create. Let us again go over here and set tiles vertically. Now in one of the viewport, let me just remove this one. Let us remove this one also. Let us maximize this one. Again go for viewport, set tiles vertically. Make sure this viewport is on where degree of freedom monitor have been mentioned. Close this one. Then for this one, okay, again I will have to go to the job manager. Click on this result button. Looks like I am not able to sync both the animation. So again let me pause it. Let me try for a second to sync the animation. Otherwise it is not necessary also. Again let me go for the viewport, link viewport manager, link viewport, go for apply and go for OK. Now let us try to select this one and now let us try to play the animation. Perfect. Now looks like both of them are in the sync. You will note at around 0.6 seconds I am getting this peak value. So this is the location from where the engagement have happened. So this will be the force which will require to push the insert into the buckle. If I go to the next frame, immediately after that it has been pushed into the buckle also. Same thing we can observe over here. Let us play the animation again. You will note after this it has been pushed into the buckle. So you can observe both the things, and at the same time if you take a look at this instance, then this is the location where the insert have been pulled out from the buckle. Let us wait for few seconds so that this yellow line will again come to this location. So observe the two things simultaneously. Now again it is pulling out. Okay, exactly this location where it have been pulled out. So basically these two forces we want to calculate. So I will pause the animation. Let us go for the probe. Then let us go for probe values. Then simply select this one and simply select this one. So to summarize, in order to push the insert into the buckle, we require around 548 Newton force, and in order to pull the insert from the buckle, we require around 612 Newton force. I hope you got the idea. So this basically ends our snapfit simulation. I hope you have enjoyed this session. To be honest with you, in this project itself, there are a lot of things that we can do additionally also. For example, the problem like this we never model fully. We always use the symmetric boundary condition in order to reduce the computational time. So from your side, additional thing that you can do is to remove half portion of this model and perform the same analysis and try to get the same answer that we have gotten. In addition to this, just for your understanding, you can go to the interaction. Let us go for interaction manager, and from here let us go for the edit. You can again run the analysis by flipping the contact. So basically you are switching the slave surface and master surface and see what additional problems you are facing. I hope you will do this iteration and put in the comment section. We will meet in the next project. Till then, take care. Goodbye.